Okay, to do problems where they want to know the pH of an aqueous solution of a weak acid or base, we can use the approximation that the concentration of HA at equilibrium is equal to the initial HA concentration minus the concentration of the hydronium ion. This is about equal to the initial concentration of HA. That is valid whenever the initial concentration of HA is greater than or equal to Ka times 100. So I'm going to use this example in a couple of exercises so you can see what that looks like. So if we take a look at class exercise number 6, it says if the Ka for a 0.02 molarity solution of benzoic acid is 6.3 times 10 to the negative fifth, determine the pH. Okay, what we're going to do is we're going to make an ice table. So you have C6H5CO2H. This is your benzoic acid, and it is in water. This is AQ for the state of matter. This is liquid. You're forming a hydronium ion and C6H5CO2 negative 1 ion. Okay? So what you're going to do here is you have your ice table. Your initial concentration is going to be 0.02 molarity, which is given in the problem. You don't have any concentration of H3O plus or C6H5CO2 negative 1 initially. And then this is minus X plus X plus X to get us to equilibrium. So 0.02 minus X, X, and X are your equilibrium concentrations. So this concentration equals this concentration at equilibrium. This concentration is going to be the initial acid concentration minus X, okay? And so if we're going to do Ka, the Ka is 6.3 times 10 to the negative fifth, as given in the problem, and this is equal to the hydronium ion concentration times the concentration of C6H5CO2 negative divided by the concentration of benzoic acid. Now, we substitute X's here, and we substitute 0.02 minus X here. So this is going to look like this. Okay, now the value of X here is really small compared with 0.02 back here. And that's because the concentration of HA initially is greater than Ka times 100. So this is 0.02 molarity. And then if you take your 6.3 times 10 to the negative fifth, which is your Ka times 100, this is going to be 6.3 times 10 to the negative third. So this is still greater than this. Therefore, you can use the approximation expression that we just mentioned. So now your Ka is going to be equal to X times X divided by 0.02. We can totally eliminate the minus X that's after the 0.02. So this is going to end up being X is 0.0011 molarity. So this is your concentration here and here. And if we substitute it here for X, you're going to end up getting 0.02 minus X, minus 0.0011. This is 0.019 molarity. Then we can finally get the pH. So your pH is going to be the negative log of 1.1 times 10 to the negative 3. Okay, which is this value here. And so your pH ends up being 2.96. All right, now, if we jump down to class exercise number 7, we're using a 0.001 molarity formic acid solution with a Ka of 1.8 times 10 to the negative fourth. Determine the pH and the concentration of formic acid at equilibrium. Now here we're going to calculate the equilibrium concentration and the pH from Ka, and we can use the successive approximations method. You can also solve it with the quadratic formula. I'm basically explaining the successive approximations method here. You can look at it in Appendix A, and we've got formic acid in water, if I make an ice table, I've got my initial concentration is 0.001 molarity. This is 0 and 0 minus x plus x plus x. 0.001 minus x, x, and x at equilibrium. Now my Ka is 1.8 times 10 to the negative 4, and that means it's this concentration times this concentration divided by this concentration. So HCO2 negative times H3O plus divided by HCO2H. So this is going to be equal to x times x divided by 0.001 minus x. Now, this original concentration of your acid isn't greater than Ka times 100. Because if you take your Ka times 100, you're going to get 1.8 times 10 to the negative second. Okay? So that means the usual approximation that we do is not reasonable. You can't drop this x. So that means we have to find the equilibrium concentrations by solving the exact expression. Now this can be solved by using the quadratic formula. Go ahead if that's what you would like to do. But we can also use something called successive approximations. Look at Appendix A if you want more information on it, but I'll give you sort of the overview. Originally, we get 4.2 times 10 to the negative fourth when we solve for x. If you put that value into the expression for x in the denominator, or of the exact expression, you're going to get and now you solve for x again. And when you solve for x again, you're going to find that x is 3.2 times 10 to the negative 4. And then you're going to put that in the denominator again. You're going to keep solving, and it's going to keep going on. And then you're going to eventually get to a point where your x is this value. So you continue the procedure until the value of x doesn't change from one cycle to the next. And in this case, 2 more cycles will give this result. And that means that is your concentration for H3O plus and HCO2 negative 1 at equilibrium. And that means that if you put that value right here, you're going to get that this is equal to 0.0007 molarity. And your pH is the negative log of 3.4 times 10 to the negative 4. You're going to get 3.47 for your pH.